Hey y'all, it's Michael with Breaking Concept again. Thank you for continuing watching this video. So in last lesson, we kind of go through about what sequence are. We did a quick recap, nothing too crazy, and I hope y'all enjoy that one. So today we're going to talk about recursive sequence. And recursive sequence is actually very important because in economics, we actually use recursive sequence to find market equilibriums. And in biology, we actually use it to do population mapping, that population dynamic, as well as finding equilibrium as well. And in pharmacokinetics, we actually use it to find dosage of, like, for example, drug concentration, etc., etc. So today, without further ado, let's kind of go through what recursive sequence is. So as you can see here, recursive sequence is basically a sequence of numbers where each term is defined as a function of the preceding terms. Now, seems like there's a lot of work here, so let me just quickly dissect this. So a sequence of number where the term is defined as a function of the preceding term. Let's take a step back and look at what we learned from last lesson. We learned that, a sequence like this, 1 over n, if we sub n to like infinity, we'll get a sequence of 1 over 1, 1 over 2, 1 over 3. Now look at the question that we see here. The question says that each term is defined as a function of our preceding terms. If you look at here closely, right, if you see 1 over 2, right, is our A2, 1 over 1 is our A1. Let me ask you a question. Is A2 dependent on A1? Right? Or is A3, which is 1 over 3, dependent on A2? The answer would be no. But what a recursive sequence would actually look like, it would look like something like this. So we're going to do an an plus 1 is dependent on an. And what I mean by that, an is our present term. We can call it an nth term, but we can also, for simplicity or understanding, we can call it a present term. So here we have a present term. And n plus 1, plus 1, so it's our n plus 1th term. As well, we can call it as a future term. So what that means is basically, there's a sequence such that our future term is dependent on our present term, as well as our present term could be dependent on our past. And let's go ahead and see one example that shows that. So here we have an amazing example. So from here we see that an plus 1 is equals to 1 over 2 times an plus 6. Just making sure this is a 6, all right? N is going to be greater than or equal to 1, and find the nth term. So basically, it's given even the first term. So an plus 1, what does that mean? It means the next term, right? The future term. So the future term of a1 would be a2. Our next term is going to be 1 over 2, and then 2 plus 6. It's 4, all right? And it's the same thing for a3. This time, a3, we have 1 over 2. Now, what do you think goes inside an? Because a3 is n plus 1, then a2 going to be n. So we're going to do a2 plus 6, which is equals to 1 over 2. And where do we find the value of a2? We just actually calculated this. So it's 4 plus 6. All right, so it's going to be 10 divided by 2, and we get 5. And that's how we do it. And we're going to find that fourth term, so we can do one more. So a4 is going to be 1 over 2, again, bracket, times our a3, this time, plus 6. And then we're going to get 1 over 2, which is, this time, a3 is 5. So it's 5 plus 6. Sorry, so it's 5 plus 6 divided by 2, that's 5.5. So this is a recursive sequence. We can say that our A4 is dependent on our A3, our A3 is dependent on our A2, our A2 is dependent on our A1, so on and so forth. So this is what we call a recursive sequence. So here we have an example of a Fibonacci sequence. And Fibonacci is a very popular Italian mathematician. And Fibonacci sequence is also as well as famous. Matter of fact, some of the Wall Street traders still use Fibonacci sequence to trade. And of course, that kind of go against, what Warren Buffett believes, but I guess that's where it gets fun. As you can see here, for Fibonacci sequence, this time, we have, look at the general formula. We have Fn equals to n minus 1, Fn minus 2. So if we just infer from the equation, we can understand that this is the previous, right, term, and then this is the previous term, because it's minus 2. So a Fibonacci sequence goes something like this. And I forgot to add the n greater than equals 3. So now we're going to start with f3. f3 is going to be equals to, as you can see here, n minus 1 is 3 minus 1 is f2, right? And then plus n minus 2, n minus 2. 3 minus 2 is 1, so f1. So from our question, we can see that f1 is 1, f2 is 1, so 1, f2 is 1, f1 is 1, 1 plus 1 equals 2. So f3 is equals to 2. Now, we can try f4. f4 is going to be equals to f4 minus 1, and that is f3. f3 plus f4 minus 2, which is 2. So where do we find f3? Right here. So we have 2 plus 1. 2 plus 1 is 3. So our f4 is 3. So we're doing more. f5, we know that f5 is equals to f4 plus f3. You can kind of get where I'm going with that one. So it's equals to 3 plus 2, which is equals to 5. So this is how Fibonacci sequence work and why it is a recursive sequence. Interestingly, a recursive sequence is also called a difference equation. Now, why is that? So let's take a look at our example from previously. We did an plus 1 equals to 1 over 2 times an plus 6. Now, if we dive a little bit deeper, we can see that an plus 1 and all this fluff here, right, it's kind of, you can just kind of simplify it into a function. And let me just write it down first. An plus 1 is going to be equals to f, the function of input, an. Because just like from my last video, when a pattern starts existing within a sequence, you can kind of make it into a function. And as you can see here, this is basically, 1 over 2 an plus 6, the 1 over 2 n plus 6 is basically a function. It doesn't really change. So all we got to do, right, is just input an, and then we'll get the value of an plus 1. So if we dive a little bit deeper, what I mean by that is if we input our current term, our output would simply be our future term or our next term. So this is our function. If we input a current term meaning an, we'll get the output of our an plus 1. So I hope this makes sense so far. And there's a name actually for this function, f. The f here is actually called an updating function. So why does it call an updating function? I mean, if you look at what just happened here, we see that if you input our current term to the function, automatically it outputs the next term. So it's just updating the value, right? You're updating an old value and you get a new value. You can see from this diagram about what's happening. And now you may be wondering, Michael, I don't see how this is a difference equation. Now I'm going to tell you why. So let's look at this one. Let's look at a variable called delta an. And delta an, we know delta just means the difference, right? Delta an is actually equals to an plus 1 minus an. Now, let me give you a quick example. For example, we have a2 equals to 4, and a3 equals to 6. So what is the difference between a3 and a2? Well, the difference between a2 and a3, which is going to be equals to 2. And we denote the previous term or the starting term as next to the delta. So delta an basically means that what's the difference between our current term and our next term. So, and to find the answer, all we got to do is take the future term and minus our present term. So we have that. And simply enough, since this is a function of an as well, we can also denote it, the delta as a g an. G is another function. We call it g. So our gan becomes our an plus 1 minus an. And notice that delta A and GAN is the same thing. So GAN, now we can call it a difference function. A difference function. And so moving forward, if we do some manipulation, we can see that AN plus 1 is actually equals to our AN plus our GAN, which actually makes perfect sense because think about it. In order to get to our next term, we need to have our current term in addition to our current distance, right? Our distance, our difference as well, to get to the next term. So this makes perfect sense, and this is exactly why it is called a difference function. And as you can see the answer here, it says the equation is formulated in terms of the difference between one term and the next. Our objective of the equation is to find the value of the next term. Remember that AN plus 1 is actually a function itself. It is what we call our updating function. So, matter of fact, we can change the whole thing to this. AN plus 1 is going to be equals to FAN, which is our updating function, and our updating function is actually equals to our AN plus our difference function. And that's super important to know as we go more in depth into like discrete time models, etc., etc. And we're going to be heavily reliant on this formula. And before moving on, let me just quickly define them again. So F, we call it the updating function, and G, we call it the difference function. So I hope you guys enjoyed this video. In the next couple of different videos, I'm going to show you how to apply these in real life scenarios, as well as showing you guys more in-depth recursive sequence, applications like equilibrium, etc., etc. So please, it is amazing. It's going to be an amazing series, so stay tuned. Thank you.